Howdy, my name is Smith, and today I'll be demonstrating you Milestone 2, which consists of NoSQL concepts, data distribution strategies, and partitioning implementation. So first, let's understand the business context. So our objective is to prepare Ethermart's data infrastructure for rapid growth and diverse data types by exploring all the NoSQL databases, and we want to implement a scalable solution by using data partitioning. So now for Ethermart, as the product and the customer data grows, then the traffic comes from different multiple channels. The relation database is actually becoming a big problem. The marketing team actually needs to analyze the unstructured reviews, and the product management wants some flexible schema for the new digital services. So this milestone is specifically to address these challenges by making the setup more scalable and exploring all the alternative database models. So our first challenge is to actually handle the unstructured data like the customer reviews that happen. We want a flexible schema for the new product types that will be coming, and we want to scale our products, customers, and orders tables because they can become huge and they can like surpass millions of records. So first, let's talk about triggers. So trigger is actually a sort of a special stored procedure in MariaDB, which is used and which is used to uh, get invoked automatically in response to a certain event on a table. So they basically get fired on like a data manipulation language statement, like some insert, update, or like a delete operation on a database. So this can be based on a certain event, like whether before or after an insert, update, or delete happens. So triggers are actually used to enforce business rules and keep data integrity and enforce them beyond the function of what foreign keys do. They can be used to perform a lot, like many repetitive tasks like audit logging, even enforcing custom business logic and derive some column updates, etc. And they are very well helpful in like preventing invalid data entry or unauthorized changes. So let me go to EC2 instance. So here I will be opening the triggers. I'm using Smith underscore DB as the database. And here, what I've defined is that if this trigger already exists, we can just drop it so that we can run this file again if we want to. And we've defined the delimiter as double slash. The default delimiter would be semicolon. Here, defined a trigger on order items to basically check the quantity so that whenever a new order item is getting created, the quantity is always greater than zero because it does not make sense to have a zero or a negative quantity. So this would be a before insert on order items. So this would be since trigger is always executed for each row separately. So here it would check if the new value of the order item, if it is less than or equal to zero, then we would signal SQL state 45,000 and set our custom error message that quantity must be greater than zero. This is another table that I've implemented. Here So here what I've done is I've since customers are used to leaving reviews for the products, what I've done is I've created a column on product table called average underscore rating. Here, what it would do is as soon as a person would leave a review, it would check the average for that product, like what is the average rating that has been given for that product, and it would automatically update uh, on the product table. So this would be like an after insert event on reviews table. And here I've basically set the average rating where I'm casting the rating as decimal and like converting that to an average. And I'm checking the product ID from the review with the product ID on the product table. So this would basically just always calculate the average rating every time a person leaves a review for that product. So here we go to MariaDB. And while we are on the topic, these are some general testing approaches for triggers. We should always use like enclose our testing approach like using the transactions like start transaction. Then we would execute our testing insert or update statements, and then we should use rollback so that we don't actually pollute the actual data which is there in the production. Rollback would basically just reverse the transaction. And we should always test our valid and invalid inputs to verify if the triggers always enforce the constraint and perform intended actions. Always check the edge cases apart from the usual valid scenarios. We should handle all the error message and signals returned by the triggers. We should, as we saw, like we can have custom error messages, and we should check the side effects, like all the updates to other tables. If, for example, we through a trigger, if we are updating some other table as well, so we should always check the side effects if there are dependencies wherever applicable. So here, let me go to the database. So here, since I've defined the first trigger before insert trigger on order items, so the order items cannot be less than zero or equal to zero. So let's say here I've tried to enter quantity as basically zero. So here you see the error message 45,000 SQL state would be thrown, and the error message would be shown as quantity must be greater than zero. So this would work similarly even on negative values. When I enter a normal value, then the insert is successful. So this was about the first trigger. Now for the second part. So for my second trigger, what I've done is I've just taken a random product ID, and here you can see the average rating for that product is 2.67, which is so far the average taken for that product based on all the reviews ratings. So what I'll do is I'll execute an insert statement, and here I would give a 5 stars. So here insert is successful for reviews. Now, if you see here, the average has changed because I gave a 5 star review. It has increased from the earlier average rating. So you can see that the after insert trigger is working as expected. Another trigger that I've defined here is the checking for the product price on products. So let's say if a person is creating entering a new product and the price entered is actually negative, so it just throws the product price can be negative. And similarly, this is for before insert as well as the before update. If someone tries to update and makes the price negative, price cannot be negative. Now here, the edge case would actually be that the price can actually be zero. We can have a product for like which is for free, and we can have a product with some positive price, but not negative price. Let's test it out. So here, if you see, I'm trying to insert a product where the price is actually zero. So here, oh, I'll just change the product ID. And it's for 51 already exists. So here I've inserted a new product, and it worked because the price was zero. Now if I try to change this to different negative value, so here the custom error throws. So this was about the triggers and the different events. Now let's talk about the operational impact analysis. So triggers are very helpful for maintaining data integrity beyond the foreign keys and automation. They always ensure the business rules are enforced consistently in the database, whatever the application level is doing. But they can also introduce performance overhead because the trigger logic must execute for every affected row. So when we have like high volume table, this would considerably like slow down insert and update operations. They complicate debugging and migration processes as well. And we also know that we can have cascading triggers where a single trigger can actually cause changes in another trigger, which could another table, which could call more triggers. So this can go on in a huge loop, thereby slowing the entire database. So we always have to keep mindful of these performance overheads for triggers. So NoSQL database actually offer flexible schema-less models that are like designed to handle large volumes of varied and like continuously changing data. They give very high flexibility and availability, which is very ideal for the modern distributed applications. So the three main motivations for using NoSQL, firstly, the scalability. They can handle massive volumes of data and high traffic loads that a single relational database just cannot handle. Flexibility because they can actually handle unstructured or semi-structured data like customer reviews or product attributes without a rigid schema. And last point is performance. So NoSQL is optimized for specific data models and access patterns. So it can give much faster like read and write speeds for certain workloads, and it is faster in terms of computation than relational single database server. So we can talk about the relevant SQL models that Ethermart can actually use. So for products, it can utilize like a document model where each product can be stored as a document in JSON, and it can capture like a flexible set of attributes such as images, descriptions, prices, and stock levels, which can all vary by category or channel. Product can also be used as like a key value model where frequently accessed product details like discounts, flags, last viewed items are stored using product IDs as keys, so that they can be like retrieved very fast. For customers, a document store can actually be used where like the customer profiles are stored as documents, which capture the preferences, loyalty points, the address history, their browsing behaviors, etc. The So that their personalized recommendation and all can be very easily documented. And a key value store can also be utilized where the authentication tokens and the session state are actually stored as key value in databases so that rapid checkout and the seamless login is possible through multiple devices. So if we talk about orders table here, the using the document store, orders, the shipment info, the payment history, the item list, all can be represented as evolving documents where it can easily be adapted for new orders or payment methods. And for key value, uh, the shopping carts can actually use like a customer ID or session ID as the key and map it to the cart contents for instant access and updates at that when they want to check out. For reviews table, similarly, or as a document store, they can put product reviews since they can be unstructured and can have images, ratings, text, etc., and even nested comments. So document databases would be storing each review as a proper like rich text and flexible document where people can like full text search and even rapid aggregation is possible. And for key value, they can actually we use the flags or like popularity counters for the featured reviews so that this would be retrieved using the review ID so that it can be quickly calculated and displayed. Now let's talk about the cap theorem. So this is basically describes the trade-off in a distributed system where it actually states that it's simultaneously like impossible to provide consistency, availability, and partition tolerance in a database system. So consistency is like all nodes can see the same data at the same time in a network. Availability means that the system always remains operational and responds to requests. It is like there's never a like network downtime. Partition tolerance would basically mean that the system continues to function despite the network failure that happens, and which is unavoidable. Like partition tolerance is always like it is something that we can always have to account for in a realistic database system. And there's no system that can guarantee that all three consistency, availability, and partition tolerance can uh, guarantee all three. So it is usually between and it we always have to account for partition tolerance. So it is usually between the trade-off between consistency and availability. So here, if you see the image, there are certain databases like, for example, which value consistency and availability, that is the traditional RDBMS system. Now, if we talk about partition tolerance and consistency here in CP, you can see databases which use like Redis, MongoDB, HBase, and Bigtable, which value consistency, that all nodes see the same data at the same time. And there are certain databases where availability takes more priority than the consistency, so that the network is never down. So in this AP category, you can see Dynamo, Voldemort, Cassandra, and CouchDB, which means basically the system is never down, even though there might be nodes where data might be outdated, but they do not compromise on availability. So that was about the CAP theorem. So let's talk about data partitioning. So partitioning basically means like dividing a large database into like smaller manageable pieces called partitions. We do this so that we can improve performance, scalability, and it's easy to maintain partitions like when we want to do specific operation on like some subsets of data. Now we have a few different types of data partitioning that we can do. Like for example, one is based on ranges, where we have a data set where we can utilize a column for range, and we want to partition based on certain year, like all reviews done in 2004 or 2005, and we want to divide it by a range. Another would be based on a list where we want to divide the data into certain fixed categories like regions or countries, etc. One would be to basically one would be hash partitioning, where we basically want uh, the hash. It would be like the entire data set would be divided into equal loads, and it would be based on basically a hash function. And there's another called key partitioning, where we want to it basically uses internal MariaDB's function instead of user defined a hash. So our task is basically to implement a horizontal partitioning on one large table to address the scalability. So we have selected the customers table where we will perform the horizontal partitioning. We would utilize the state column to partition it by using list partitioning. And here we would retain the customer ID as the main identifier. It would be part of the primary key of the partition table. Why we have chosen customer? Because customer table is used, and it would often take like have millions of rows in realistic scenario. And people would actually like for analysis, queries would often utilize the location, like all the customers from Texas or all the customers from New York or New Jersey. So partitioning by state would actually help the partition pruning, so that only the relevant partitions are scanned based on the region or the state. And this would clearly demonstrate the columns partitioning feature of MariaDB. And here what we'll do is we'll create a separate partition table and migrate the data from the original customers table to this table. So we will be maintaining the integrity of the original customers table, which has the foreign keys. And here we would have like a shadow partition table just for the scalability analysis. So here our strategy would be to create a customers partition as a shadow table. And here the primary key would include the customer ID as well as the state, which would be the composite key. Now it is a MariaDB like a mandatory rule that it would require the partition column to be in the primary key itself. So it would be a composite key utilizing customer ID and state. And here we would basically define list partitions like TX would be Texas, CAV California, and by New York, FL, and an other option for all the remaining states just for our demonstration. So I would quickly go to the file where I've done the implementation. Here, this is the table that would be created, and it lists all the columns. So here, if you see the primary key is defined as the customer ID as well as the state, it should be part of the primary key, the partitioning column. Here, I've defined the partition values on four states for now. and the other would be contained in just the other as the character. So here, what I've done is like we've done some normalizations where if data consists of like lowercase or uppercase, different types of the way like the states are written, it would all normalize it into standard formats. Like even if it's all lowercase or uppercase, it would all normalize it to just TX. And after the partitioning is done, we just quickly check and query the partition. We'll show the count and we'll just show the partitions for the Texas as well as the California and New York. And here this code is to just handle if there are any duplicate rows which actually map to multiple partitions for a single like a same customer. They would be handled appropriately. So if you see the partition here, this we have done for based on four states and an other partition for all the remaining states. We've utilized a case expression to insert and like normalize the state values as I discussed, different way that states are mentioned. We would be verifying the partition pruning, and this is after I run like after the code is run, we can just verify it using the command explain partitions, and we just mention the table and the state using the where. So let me go to MariaDB. So here, if you see, I've queried the customers a partition which are from Texas, and this shows the table and the value, the information about the partition, like key, possible keys, the type that it is, the number of rows for this partition, etc. And here, if you see, the original customers table remains intact with the relationships. The partition version is just for the performance demo, so we have not broken any foreign key relationships in the original table. Now let's talk about column store. So column store is actually an analytical engine which stores the data in the column format. So the traditional storage, like we do it row by row, but here this is optimized for transactional queries, and it is very efficient. Like we do the storage like by column instead of a row. So each column is actually stored in a separate file, and each column for a given row is at the like same offset. So this is actually very highly efficient for aggregations, joins, and complex analytical queries. And this is like it can actually compress data more effectively and read like the necessary columns only for a query. So this would like help like reduce the computation like overhead and reduce the input output like computation. So some suitable scenarios for Ethermart for this. So for marketing analytics, if you want to like analyze total sales by product category over time or calculate the average order value across like different sales channels, then one would be for like product performance, where we want to determine which products are performing best on which sales channel, or like we want to understand the sales trends of a new product line. Then customer insights, where we want to like run complex queries on a vast customer database and we want to identify purchasing pattern or like segment customers for targeting campaigns. So like column store would actually be a very good fit for Ethermart's need for like running the complex and very heavy like analytical queries for against like the millions of data sets that are generated by their multiple channels. So it can be a very good consideration for a separate analytical data store to like offload these data sets like and workloads from the main transactional MariaDB database. So so far in this demonstration, we have talked about the context of implementing um, the triggers. Then we talked about their operation impact analysis. We talked about motivations for NoSQL and the different models that are can be relevant for Ethermart based on NoSQL. We talk about the CAP theorem. We also demonstrate the data partitioning, the implementation strategy, and we talk about column store and the suitable scenarios that are applicable for Ethermart. So through this demonstration, I've utilized the LLM, basically a combination of Perplexity and Gemini to assist with the SQL trigger logic and getting the initial script for the data partitioning. Now, the code given by AI actually had fixed a certain syntax errors, like it instead of like it gave basically a default value for partition, which actually MariaDB does not support. So that had to be handled by giving others as a value as well. And it also did not initially provide the state inside the primary key definition, which is like a mandatory rule for MariaDB. The primary key needs to have the partition column. So yeah, these are some of the syntax and the some changes that were made in the SQL script by after the AI generated the initial code. So yeah, these are some good lessons learned that the list partitioning, it actually does not support a catch-all default. We all need to map it to a value explicitly like other. And we need to always test the AI generated script because once we get the code, we can like once we analyze, we can actually get a deeper understanding of the issues that can happen through the initial scripts. So it was very beneficial for accelerating the initial code generation for the partitioning and the trigger, so that the time, like the deliverable time was reduced. But we still needed the manual fixes, like if you see the limitations. So it used to like assume MySQL syntax rather than MariaDB, so it always needed to be changed. The prompt needed to be changed, and it could like function. It gave functionally flawed code as multiple times, even when checking the triggers script as well. So it is always good to understand the SQL logic and business requirements to properly debug and refine the output. So the final impact was like it gave a good working partition, customer stable, and implementation. It helped me understand and debug SQL concepts and increase my confidence in debugging and adapting scripts for MariaDB. And it helped it basically improve my efficiency using AI for initial setup tasks and gave me a better, deeper understanding of concepts. So the code was not just correct, but also optimized and secure. For references, I've utilized some websites for images as well as Gemini AI and Perplexity for the SQL scripts. Thank you so much.